So here we go. This is the wind-driven coastal upwelling. And just go slowly, step by step, of what happens. So I activate the pointer is on. See, the pointer is on. Let's have a look at the top graph. This is a transect, a vertical transect. The y-axis shows you the depth from the surface to 100 meters. The x-axis is distance from the coast, and you can see the density field. Red is heavier water, blue is lighter water, and you can see that the red water is moved in the model to the surface, and this is what we call full upwelling. Okay? This is what you see in the density field. The second graph shows you the onshore, offshore velocity component. You can see near the bottom, it's onshore. This is the bottom Ekman layer, onshore movement. And near the surface, you see the offshore movement in the surface Ekman. You can see some overlap very close to the coast. The third panel here shows you the alongshore velocity component, and you can see a upwelling jet. This is a coastal upwelling jet which does not reach the seafloor. It's detached from the seafloor. It's near the surface. Okay? So this is what happens, the upwelling jet. And the bottom panel is just an indication on how strong is the mixing. And you don't see much big numbers here. It will be different on the next slide. What you can also do with the model, you can actually work out what is the shear stress at the seafloor. How big is the shear stress? Remembering that you need something like 0.3 Pascal to actually erode sediment. And this is behind my head. Here are time series of the shear stresses that develop at different locations. So the x-axis is time from 0 to 10 days actually. Okay? And the vertical axis is the shear stress. So if you start, there's nothing happening, no currents yet. The model has no currents at the beginning. And then after, at 20 kilometers away from the coast, you get a maximum shear stress of 0.2 pascals until the end of the simulation. Okay, at 4 kilometers you get, this is 20 kilometers. At 4 kilometers, okay, it's a little bit, okay, you only get even much lower. Okay, and why the bed shear stresses are actually relatively low is because you have stratification in the inshore area. Okay? So now what happens here in that is you can see that the upwelling circulation extends to very shallow water. This is one key take-home message. Okay, so you really get the movement of shelf bottom water into the euphotic zone near the coast, straight near the coast, and this agrees with observations. And you have relatively low bed shear stresses, so there is no interaction with the seafloor. However, the organic matter that is formed near the surface falls somewhere back onto the seafloor. Not necessarily in the same direction, but it can accumulate on the seafloor, so you actually have a source of nutrients, okay, accumulating on the seafloor. So now let's switch the wind direction into a downwelling favorable wind, and let's see what happens.